2-point charges A and B having charges plus q and minus q respectively are placed at certain distance apart and the force acting between them is F. Okay, so we have this charge plus q and minus q, so force between them is F. Okay, now if 25% charge of A is transferred to B, then the force between charges becomes. Now what will happen? This is the question. Okay, so this is plus q minus q. This is A and B. Okay, so now when 25% charge from A is transferred to B. Okay, so from here to here. So 25% means what? 1/4, right? 25% means 1/4. So 1/4 of charge is transferred. How much charge will be left? 3q by 4. Okay, and distance between them is same. So this is positive 3q by 4. Now you are transferring plus 3q by 4 here. So what will be the charge here? It will be minus q plus, not 3q by 4, plus q by 4, right? So it will be minus 3q by 4, the charge here, minus 3q by 4. Okay, so if distance is same, this force F is directly proportional to product of two charges, q multiplied by minus q, you can say, and F dash would be proportional to what? 3q by 4 multiplied by minus 3q by 4. 3q upon 4 multiplied by minus 3q upon 4. Okay, so if you divide these two, then what do you get? F dash upon F will be equal to, so this q square and q square, negative sign, it will get cancelled. So it will be just 3q by 4 square. Okay, so it is 9 by 16. That means F dash is equal to 9f divided by 16. That is option C. Let's see next one. Suppose the charge of a proton and an electron differ slightly. Okay, charge on proton and electron, they differ slightly. One of them is minus E, the other is E plus delta E. If the net electrostatic force and gravitational force between two hydrogen atoms placed at a distance d much greater than atomic size apart is 0, then delta E is of the order of. This is a question that you have two hydrogen atoms. Okay, so hydrogen atom has a proton and an electron, and this is first hydrogen atom. So how much is charge on proton? Given that it is not E, it is E plus delta E. It is E plus delta E. Okay, and okay, so this is one hydrogen atom. So how much would be the net charge on hydrogen atom? E plus delta E minus E. So plus E and minus E gets cancelled. So net charge is delta E. Okay, so you have two such hydrogen atoms. They are placed at a distance d, which is very large compared to the atomic size. Okay, so these are suppose two hydrogen atoms. Charge on this one is delta E, charge on this one is delta E, positive. Then what happens? What happens is the force between them is 0. So there will be some repulsive force, repulsive electrostatic force, and there will be some gravitational force which is attractive. Okay, So electrostatic force is repulsive, gravitational force is attractive. If they cancel out each other, then the net force will be 0, right? So how much is electrostatic force? We'll say uh, force due to the electrostatic force is F suffix E, gravitational force is suppose F suffix G in magnitude. One is attractive, one is repulsive. So they will cancel out each other. Okay. So this is K multiplied by Q1, Q2. So which is delta E into delta E divided by R square, and gravitational force is G multiplied by M1, M2 upon R square. So it's given that mass of hydrogen is this much. Okay. So mH square, mass of hydrogen square upon R square. So R square and R square gets cancelled out, and we want to find out delta E. So delta E square is equal to G divided by K multiplied by mass of hydrogen square. Okay. So what is G? The value of G is 6.67 multiplied by 10 raised to minus 11. 6.67. So this is equal to 6.67 into 10 raised to minus 11. Okay, mass of hydrogen is 1.67 multiplied by 10 raised to minus 27. So we just want order of magnitude. Okay, this is 10 raised to minus 27, and we have square of that divided by K is 9 multiplied by 10 raised to 9, right? So let's find out the order of magnitude. So this is of the order of 10. Okay, this is of the order of 10. 10 multiplied by 10 raised to minus 11 is 10 raised to minus 10. Okay, and this is also what, 10 raised to plus 10. If we take it in numerator, it will become 10 raised to minus 10. Okay, so delta E square we have 10 raised to minus 10 square multiplied by 10 raised to minus 27 square. That means delta E is of the order of, okay, it is of the order of, right, it's not equal to, it is of the order of this thing. 10 raised to minus 27 multiplied by 10 raised to minus 10. That is minus 37 is the answer. Option B. Okay, it is 10 raised to minus 10 plus 27. That is 10 raised to minus 37. A particle of mass m and charge q is placed at rest in uniform electric field E. So electric field is uniform, not changing, and then released. Then the kinetic energy attained by particle after moving a distance y is. So see, there is a particle, it's in uniform electric field. So electric field is constant. Okay, this is electric field, it's directed like this. So these are electric field lines shown to drawn to show a uniform electric field. So they are equidistant. That means lines are equally spaced. So that means the electric field is uniform. They are directed in same direction. Okay. So now you keep a charge here. So what will happen? Charge gets pushed by the electric field in this direction. Okay. So there is force on this charge due to the electric field, right? Force is equal to Q into E, because E is equal to F upon Q. Force is equal to Q into E. Okay. And now it moves through some distance y. It moves through this some distance y. So there is some work done. Work done is equal to force into displacement, because force is constant. Okay, electric field is uniform. So it is equal to F into y. Okay, so it is Q into E multiplied by y. And then this work done gets stored as kinetic energy of the particle, right? This particle was at rest, it is pushed by electric field. Okay, so it gains some energy, kinetic energy. So it is equal to work done by the electric field on the particle. Okay, so this is the answer. QEY is the answer. Toy car with charge Q moves on a frictionless horizontal plane surface under the influence of uniform electric field. So there is a car which has charge Q. It moves on a horizontal surface under uniform electric field E. Due to the force QE, its velocity increases from 0 to 6 meters per second in 1 second duration. Okay, so velocity increases from 0 to 6 in 1 second. At that instant, the direction of field is reversed. Okay, so for 1 second, electric field is directed like this. So it moves, let's suppose, from here to here. Okay, right? This is for 1 second. So this is electric field, and this is the car. Moves from here to here in 1 second. This is toy car. Then, when the car is at this position, okay, so car has charge Q. When it is at this position, the field is reversed. This is given. Field gets reversed. Okay. At that instant, the direction of electric field is reversed. The car continues to move for 2 more seconds. It continues, yeah. Let me explain it once again. So you have this car, okay? You have a toy car which is kept in uniform electric field, and this car has got charge Q. Okay, the car has got charge Q on it. So it is just placed there, right? It is just placed. So now, due to this electric field, because electric field will exert some force, car will move from this point to this point. Okay, it moves in 1 second and it gains this much speed, right, from 0 to 6 meters per second. Now, when it reaches this point in 1 second, the field is reversed. Okay, so now electric field acts in opposite direction. So now what will happen? So it keeps on moving for 2 more seconds, and the average velocity and average speed of the toy car between 0 to 3 seconds are respectively. This is the question. Okay, so now what will happen? The field is reversed. So now see, it has gained this much speed, this much velocity due to this electric field. Now, if you exert opposite force, equal and opposite force, so its velocity will go from whatever it is to 0 in same amount of time, right? So it will go to some position. Actually, it will travel same distance and stop. So this will happen in, okay, this has happened in 1 second. So this will again happen in 1 second, right? But it continues to move for 2 more seconds. This is given. So what will happen in next second? This is 2 seconds. Okay. So after 1 second, it keeps on moving till 2 more seconds. So 1 second plus 1 more second. So now it has stopped here, but electric field is acting in same direction. Okay. So it will move like this. It will move from here to here, then from here to here, and from this point it will move. So it will not take turn like this. It will move backwards from here to here. Again in 1 second, it will gain same velocity. Got it? In 1 second, it will gain same velocity. Okay. So now, question is average velocity and the average speed of toy car between 0 to 3 seconds. So to find out average velocity, we need to find out this displacement. Okay, so car moves from here to here, and to find out average speed, we have to find the distance. So the total distance is 3 times of this displacement. Okay, so let's do that. So how much is acceleration? acceleration is, if we consider this thing, it goes from 0 to 6 meters per second in 1 second. So acceleration is v minus u divided by t, that is 6 minus 0 divided by 1, 6 meters per second square. Okay, so now we know how much would be this displacement. So it is s is equal to ut plus half at square, right? It starts with 0 velocity, so this thing is 0. Okay, this thing is 0, and this is equal to half of a, acceleration is 6 multiplied by t square, t is 1, so it is 3. Okay, so how much is velocity now? So why did I find only this much distance? Because it will come back at the same point after 3 seconds. Okay, so what is velocity? It is displacement divided by time. So it is s upon t. How much is that? 3 upon 3. So it is 1, right? 1 meter per second. But how much would be speed? So this is its displacement, but it has covered this much distance actually, from here to here, plus here to here, plus here to here. Okay, so it is 3 times. So speed is distance upon time, that is 3 times 3. So 9 upon 3. So it is 3 meters per second, right? So option B is the answer. An electron falls from rest through a vertical distance h in uniform and vertically upward directed electric field E. Okay, so electric field is directed like this, and you release an, this is an electric field, you release an electron and it falls like this. Okay, now the direction of electric field is now reversed, keeping its magnitude same. So now you have electric field like this, its magnitude is same. The proton is allowed to fall from rest in it through the same vertical distance h. Okay, so this is a proton, E plus, this is proton. So electron falls through distance h, okay, till here. Proton also falls to the same distance. The time of fall of electron in comparison to time of fall of proton is, option A is smaller, option B is 5 times greater, option C 10 times greater, option D equal. Tell me. This is quite recent, 2018. But acceleration of electron would be force divided by mass of electron, and acceleration of proton would be force upon mass of proton. Mass of electron is much smaller compared to mass of proton. Okay, and that's why acceleration of electron would be very large compared to acceleration of proton. And that's why what will happen, the electron will fall much faster compared to the proton. So time taken by electron will be much smaller. It's option A. So next question is, point charges plus 4q, minus q and plus 4q are kept on x-axis at point x equal to 0. Okay, so at x equal to 0 there is charge plus 4q. At x equal to a there is charge minus q, and x equal to 2a, okay, you have plus 4q, right? Then only minus q is in stable equilibrium. All the charges are in stable equilibrium. All of charges are in unstable equilibrium. None of the charges is in equilibrium. So what will happen? So let's suppose only these three charges are there and nothing else is there. So see, if we think about the force acting on plus 4q, So there is an attractive force due to minus q. There is a repulsive force due to plus 4q. Okay. Similarly, on this charge, there is an attractive force due to minus q. There is a repulsive force due to this plus 4q. Okay. So net force on this charge and this charge would be repulsive. So they will be pushed away. They will be pushed away, right? But what about this charge? So see, small q, it is pulled by this charge and it is pulled by this charge. And since these two charges are equal, okay, since these two charges are equal and the distance is also equal, okay, the distance is also equal from this charge. So what will happen? I mean, the net force on this charge is 0. Okay, the net force on this charge is 0. So that means this charge is in equilibrium. Got it? So none of the charges are in equilibrium is wrong. Okay, all charges are in equilibrium is also wrong. All of them are not in equilibrium. Okay, so all of them are neither in stable or unstable equilibrium. So option A is only correct. The charge minus q is in stable equilibrium. Let's see next question. A charge q is placed at a center of line joining two equal charges plus q. The system of three charges will be in equilibrium. Q is equal to. Okay, so charge small q is there and it is placed at the center of line joining two charges q and q. Okay, so then the system will be in equilibrium if q is equal. So now what you have to do is you have to find force on any other charge, because see, this charge will be in equilibrium, right? Because see, it is at same distance from this charge. Okay, it is at distance r. Let's suppose from this charge also it is at distance r, because we have kept it at the center. So this will be in equilibrium. There is no question about it. So now other two charges should also be in equilibrium. So force on this one should be equal to 0, net force, and force on this one should also be equal to 0. So let's calculate force on this one. So force on first charge. Okay, force on first charge. So it is k multiplied by q into q divided by r square, plus it is force on this charge due to this charge, plus k multiplied by k is 1 upon 4 pi epsilon naught q into q divided by how much is this distance? 2r, 2r square. Okay, and this net force should be equal to 0 for that to be in equilibrium. So then we can divide by q. Okay, sorry, then we can divide by k. It is q into q divided by r square plus q into capital Q upon 4r square is equal to 0. R square gets cancelled, q and q gets cancelled. Okay, so that means q plus q by 4 is equal to 0. That means q is equal to minus q by 4. Okay, so this charge should be of opposite nature and it is equal to minus q by 4. So option A is the answer. Yes. Okay, so this is also a simple question. Next question. When air is replaced by a dielectric medium of constant k, the maximum force of attraction between two charges separated by a distance. Option A increases k times, remains unchanged, decreases k times, increases k times. So if air is replaced by some other medium, what will happen? So we have force in air is 1 upon 4 pi epsilon naught. Air is almost same as vacuum. Okay, multiplied by Q1 Q2 upon R square. And if some other medium, so for some other medium, it will be 1 upon 4 pi epsilon naught K. Okay, they have written it capital K. So multiplied by Q1 Q2 divided by R square. So it is inversely proportional to the dielectric constant, right? So that means if dielectric constant K is more, what will happen? The field will, the force will decrease K times. Okay, so answer is it decreases K times. It's inversely proportional, so it is option C. Let's see this one more question. Two positive ions, each carrying a charge small q, are separated by distance d. If F is the force of repulsion between the ions, the number of electrons missing from each ion will be. Okay, this is the question. So F is the force. So you have two positive ions, right? So some electrons are removed from them. Some electrons are removed from the atoms, so they become ions, right? So it can be 1 electron, 2 electron, 3 electrons. Okay, so atoms are neutral. When you remove electrons, they will become positively charged. So how many electrons are removed? So charge on this one is q, charge on this one is also q, distance between them is d. Okay, so if n electrons are removed, q will be equal to n times e, that much positive charge, right? So force can be written as 1 upon 4 pi epsilon naught, because there is 4 pi and epsilon naught in all options, multiplied by q square upon d square. Okay, because both of them have same charge. So this is equal to 1 upon, we can write q square equal to F multiplied by 4 pi epsilon naught into d square, right? And therefore q square is n square e square, because q is equal to ne. It is n square e square is equal to this thing, F multiplied by 4 pi epsilon naught d square. If you take n square on other side, sorry, you take e square on other side, we want to find out n, right? How many electrons are removed? So we'll take e square on other side. Okay, and then we'll get square root because we want n. So it will be square root of this thing. Okay, it's option C. 4 pi epsilon naught F multiplied by d square divided by e square. So let's see the let's see first question. 3-point charges plus q, minus 2q and plus q are placed at points. So these are the points. X is equal to 0, y is equal to a, z is equal to 0. Then x equal to 0, y equals to 0, z equals to 0. And x equal to a, y equal to 0, z equal to 0 respectively. The magnitude and direction of the electric dipole moment vector of this charge assembly are. Okay, so we want to find out the resultant dipole moment of these charges. So first charge is at x equal to 0, y equal to 0, z equal to 0. Second one is at, y is equal to a. Okay, this one is at x equal to 0, y equal to 0, z equal to 0. So this one is at origin. And x equal to a, y equal to 0, z equal to 0. So z coordinate for all three is 0. That means the charges are kept in xy plane only, right? Since z coordinate is 0. Okay, so let us draw these charges. So x is equal to 0, y is equal to a. So you keep that first charge. So let's suppose this much distance is A. Okay, and you keep charge plus Q here. Then second charge is minus 2Q. So it is at origin. So minus 2Q is here at origin. And x equal to A, y equal to 0, z equal to 0. So x is equal to plus A. So there you keep another charge plus Q. Okay. So now there will be some dipole moment from negative charge to positive charge. So you take one of these two negative charges. Okay, you take minus Q. So there will be a dipole moment from minus Q to plus Q, and a dipole moment from another minus Q to this plus Q. Okay, and dipole moments will be directed like this. So this will be, let's call it P bar. This one is P bar. Okay. So now how much would be the net dipole moment? So net dipole moment is vector sum of these two. So it will be directed like this because the magnitude of both of these is equal. It will be directed like this. So resultant would be in this direction. Okay. 45 degrees. Okay. So this is resultant. And how much would be resultant? So it will be just, so let's suppose this is P dash. Okay. This is P and this is P. So we can keep it here also. So this is P dash. Okay. P dash bar. This is P bar and this is P bar. Okay. So using Pythagoras theorem, we can say that P dash square is equal to P square plus P square, right? Then it is 2P square. So therefore P dash is equal to square root of that. Okay, so it is equal to 2 times, sorry, square root of 2 times P. Okay, and what is P? So P is equal to Q multiplied by distance between the charges. So distance between charges here is A. Okay, so this much distance is A, right? So it is, this is equal to square root of 2 multiplied by Q into A. Okay, so we have habit of writing this distance as 2A, but here the distance is equal to what? A. Got it? All right. So this is the magnitude, and what will be the direction? So let's check. It is directed along x equal to 0, y equal to 0, z equal to 0, and x equal to a, y equal to a, z equal to 0. Okay. So actually this one would be answer. Okay. Why? Because see, this point is at x equal to 0, y equal to a. So this much distance is a. This much distance is also a. So this dipole moment would be directed in this direction, right? Along this line. So what are coordinates of this point? So if we think about xy plane only, x coordinate is a and y coordinate is also a. So it is a and z coordinate is anyway 0, right? So this is a 0. So in what direction it is directed? From 0 0 0 to a 0. Okay, got it? Yes, no. Let us see next problem. A point Q lies on the perpendicular bisector of an, sorry, a point Q lies on the perpendicular bisector of an electrical dipole of dipole moment P. If the distance of Q from dipole is R, much larger than size of the dipole, then electric field at Q is proportional to. So tell me, this is very simple. lies on perpendicular bisector. So this is your dipole, minus q plus q, and point lies on the perpendicular bisector. That means it is on equator. Okay, so this is point P. This is some point. Okay, let's call it C. So the electric field at this point, it is proportional to, what is the electric field at equator? So E equator is 1 upon 4 pi epsilon naught multiplied by P upon R cube or X cube, you can say. So it is directly proportional to P, inversely proportional to R cube. So it is option D. Okay, let's see next question. I guess there would be some network issue or something. Don't know. An electric dipole is placed at an angle of 30 degree with an electric field intensity 2 multiplied by 10 raised to 5 Newton per coulomb. It experiences a torque equal to 4 Newton meter. The charge on the dipole, if dipole length is 2 centimeter, is. This is very simple question, right? Because we are given that there is dipole kept at an angle 30 degree with electric field. So this is electric field and it experiences torque. So everything is given. Okay. So we know tau is equal to PE multiplied by sine theta. Okay. And we want to find out charge on the dipole. So it is, okay. So charge is suppose Q. So P is equal to what? Q multiplied by 2A into E sine theta, and we want Q, so we'll take all other things on other side. So it is tau divided by 2A multiplied by E sine theta. Okay, right? So torque is given. Torque is 4 Newton meters. Okay, so 4 divided by length is given. It's 2 centimeters. Okay, it's not A, it is 2A. Okay, so 2 multiplied by 10 raised to minus 2 multiplied by electric field is 2 into 10 raised to 5 and sine theta, sine 30 is half. Okay, so this 2 and 2 gets cancelled. 10 raised to 5 multiplied by 10 raised to minus 2 is 10 raised to 3. Take it in numerator, it's 10 raised to minus 3. So 4 upon 2 is 2. So the answer is 2 multiplied by 10 raised to minus 3 coulombs. So that is 2 millicoulombs. Okay, option B. Next question. A dipole of dipole moment P bar is placed in uniform electric field E bar, then the torque acting on it is given by. Okay, so dipole is kept in uniform electric field. What is the answer of this question? It is option B. Right, this is just formula. Okay, so we have to remember this formula. Okay, we have to remember all the formula actually. Next question. What is the angle between the electric dipole moment and electric field strength due to it on equatorial line? Tell me. Option A, 0 degrees. It is 180 degrees. Okay. So electric field at equatorial point. Okay, electric field at equatorial point is directed opposite to the dipole. This is minus q plus q. Okay, so dipole moment is directed like this, and the electric field is directed opposite to that. Okay, this is electric field. So how much is angle between them? It's 180 degrees. Okay, yes, no. Tamil Selvi, what's the formula? E equatorial is equal to 1 upon 4 pi epsilon naught multiplied by minus p bar divided by r cube, or if we call this distance x, then x cube. So how much is angle between them? It is 180 degrees because we have this negative sign in formula. Okay, this is simple, right? Next question. An electric dipole of dipole moment p bar is placed in uniform external electric field E bar. Then option A, torque experienced by dipole is E bar cross P bar. Okay, this is not true. It is P bar cross E bar. Torque is 0 if P bar is perpendicular to E. So is this true? Torque is equal to PE sine of theta. Okay, angle between them is 90. Then torque is maximum actually. Okay, so if this angle is 90, then sine of 90 is 1. So torque is maximum. Okay, so this is not true. Option C, torque is maximum if P bar is perpendicular to E bar. This is true. Okay, so this is the answer. Then potential energy. So we didn't learn about potential energy. We'll learn about it in next chapter. Okay, all right. So we don't need it here. Answer is option C. Torque is maximum if P bar is perpendicular to E bar. Right? The electric field at a point due to an electric dipole on an axis inclined at an angle theta to the dipole axis is perpendicular to dipole axis if theta is. Okay, so this is the question. So electric field is perpendicular to dipole axis if theta is. So see, this is suppose our dipole, and this is the point where we want to find out the electric field. Okay, this is minus q, this is plus q, and this is the dipole moment. Okay, direction of dipole moment. This angle is theta, this angle is theta. Okay, so we want to find out electric field at this point, right? So what we had done is we had resolved this dipole along two perpendicular axes. Okay, so one along this one. So what was the component? So we can draw it like this. Okay, so this is P cos theta. Okay, and for this component, the electric field, sorry, for this component, this point is, it lies on the axis. Okay, so there will be some electric field due to this component, this dipole moment, and then the other component we have is directed like this. Sorry, is directed like this. Okay, so this one would be P sine theta. For this component, the electric field at this point is, sorry, for this component, this point is equatorial. Okay, so we can say that there would be some electric field due to this component at this point. What will be its direction? It is directed like this only. So this dipole moment is directed like this. Okay, for axial point, we know the electric field is in same direction as that of the dipole moment. Okay, so the electric field due to this component is directed like this. So let's call it E parallel. we called it E parallel. Okay. And then what about this component? So for uh, the equatorial point, the direction of electric field is opposite. Okay, it is opposite to that of the dipole. So this one would be E perpendicular. This one would be E perpendicular. So net electric field is vector sum of these two. Okay, net electric field is vector sum of these two. So it will be directed something like this. So question is, the angle between this dipole and the net electric field is 90 degrees. So suppose this angle is something, okay, this is theta, suppose this is beta or something, okay. So this angle, because see, if this is perpendicular to this, that means this angle plus this angle is how much? 90 degrees. Okay. So theta plus beta is equal to 90 degrees. Right? Got it till this point? Yes, no? Okay. So then we have to find out this beta. Okay. No, we have to find out theta only. All right. So see, what would be E perpendicular? What is formula of E perpendicular? It is 1 upon 4 pi epsilon naught. Let's call it K only, multiplied by P upon R cube. Okay, this is the formula. But it is caused by this component. It is not P, right? This dipole moment is not P, it is P sine theta. So it's P sine theta divided by R cube. Okay, and what is E parallel? Is electric field due to this component of the dipole. So it is K multiplied by 2 times the dipole moment upon R cube. Okay, for axial point, the electric field is K constant, that is 1 upon 4 pi epsilon naught multiplied by 2p upon R cube. Okay, but it's not P, this is P cos theta, right? Now see, you want to find out this angle beta. So what would be tan of beta? So this is, okay, if you put it here, so this becomes opposite side. Okay, this is the adjacent side. Okay, if I put this E perpendicular here, okay, this is E perpendicular. So tan of beta is equal to E perpendicular divided by E parallel, sorry, E parallel. Okay, so if I divide this by this, what do I get? So K P R cube will be cancelled. It is sine theta divided by 2 cos theta. Okay, so it is sine theta divided by 2 times cos theta. So that means it is half of, okay, so tan beta is equal to half of tan of theta. Okay, this is what we get. Half of tan of beta, sorry, tan of theta. Okay, and what about, all right, so we know this relation that theta plus beta is equal to 90 degrees. Okay, can we relate tan of theta and tan of beta? Okay, these two are complementary angles, right? So for complementary angles, we know tan of one angle is equal to cot of the other. Okay, sum of two angles is 90 degrees. Then tan of one angle is equal to cot of other angle. Okay, so tan of beta is equal to, I can say, cot of theta. So I can substitute cot of theta here. Cot of theta is equal to half of tan of theta. That means I can move this on this side. Sorry, this is not cos, it's cot. Okay. So this is 1 upon tan theta. You can move it on other side. So you get tan square theta equals to 2. That means tan of theta equals to root 2. Okay. And therefore theta equals to tan inverse of root 2. This is the answer. Tan inverse of root 2. It's option C. See, most of the questions are simple. Okay, most of the questions based upon the electric dipole are simple. There are some questions like this which are little bit tricky. Okay, but once in a while. And it is not from Neet. Actually, in Neet, there were 3, 4 questions only. So first 4 questions that we discussed, they were from Neet, and all other questions. I thought 4 questions is very less, right? So all other questions are from some different exams. Okay, but that doesn't mean there cannot be a question. Okay, these are uh, actually 3, 4 topics. So let's see next question. The electric field due to an electric dipole at a distance r from its center in axial position is E. Okay, so E axis is equal to E. If dipole is rotated through an angle 90 degree about its perpendicular axis, then the electric field at same point will be. So this is very, very simple. Right. Dipole is like this. This is your dipole. Okay. Minus Q plus Q. And the electric field at an axial point at this point. Okay. The electric field due to this dipole is E. So right now this is an axial point. Now if dipole is rotated through 90 degrees. So if you rotate this through 90 degrees, what will happen? About its perpendicular axis. Okay, about a perpendicular axis. So the axis is perpendicular to plane of this paper, you can say. Okay, so the dipole, new position of dipole will be like this, right? So this is plus Q minus Q, or okay, this will be minus Q and this will be plus Q depending upon how you rotate it. So it's rotated by 90 degrees. Okay, so this point will be at equator now. So how much would be the electric field there? It will be half of the earlier electric field, right? Because E equator is equal to half of E axis. Okay, now the point has become equatorial point. So it is half of E, right? Option C. So this one was extremely simple. Next question. Charge is situated charge is situated at a certain distance along the axis of electric dipole experience a force F. Experiences a force F. Okay. So when charge is on the axis, it experiences force due to dipole. It is F. The distance of charge from dipole is doubled. Then the force acting on it will become. Tell me. Okay. See, this is dipole. Okay. And keep some charge on the axis. Okay, so this is charge, some, okay, let's call it delta Q or something. Okay, so this is minus Q, this is plus Q. So now there will be some electric field due to this dipole at this point, right? So electric field is E axial. Okay, so electric field due to dipole at this point is E axis. How much would be the charge? How much would be the force acting on delta Q? It is the charge multiplied by electric field. Okay, so it is E axis multiplied by delta Q, which is equal to 1 upon 4 pi epsilon naught multiplied by 2p upon r cube multiplied by delta Q, right? Now what you are doing is you take this charge, move it at twice the distance. Okay, so what will happen? So distance is doubled, force becomes F dash, suppose. So force is inversely proportional to r cube, right? Force is some constant, this constant upon r cube, because charge will remain same, dipole moment is same, everything else is same. So it is inversely proportional to r cube. Okay, so you can say F is equal to k upon r cube. So F dash will be equal to what? K divided by 2r cube, because distance has become 2r now. So that is k upon 8r cube. Okay, and what is k upon r cube? It's F. So this is equal to F upon 8, option D. So this is very simple question. Next one, the electric field and the potential. Okay, so sorry for taking this question. But anyways, the electric field and potential of an electric dipole vary with distance r as. Okay, so the electric field due to dipole is inversely proportional to r cube and the potential is inversely proportional to r square. We'll learn it in next chapter. Okay, so the answer of this question is 1 upon r cube and 1 upon r square. It's option D. We learned this, that potential of electric dipole is inversely proportional to r square. A spherical conductor of radius 10 centimeter has a charge of 3.2 multiplied by 10 raised to minus 7 coulomb distributed uniformly. What is the magnitude of electric field at point 15 centimeter from the center of the sphere? And this is the question. Okay, so you have a spherical conductor of 10 centimeter and it has charge of 3.2 multiplied by 10 raised to minus 7 coulombs distributed uniformly. Okay, so Q is given 3.2 multiplied by 10 raised to minus 7. Then what is the magnitude of electric field at point 15 centimeter? So radius of this spherical conductor is 10 centimeters. You want to find out the electric field at 15 centimeters from the center. So actually we have not seen this. Okay, but we'll just directly use the formula. We'll see this tomorrow. Okay. So the electric field due to a spherical conductor outside the conductor is given by 1 upon 4 pi epsilon naught multiplied by q upon r square. Okay, so suppose this is a conductor, suppose this is a spherical conductor and there is some charge on this conductor. Then for all outside points, this conductor acts as if there is a charge plus q kept at the center of that conductor. Okay, so it just acts like a point charge, and that's why this is the formula for the electric field. So we'll see this tomorrow. Okay, so actually we should have seen this question tomorrow only. But anyways, this is the formula. So we just have to substitute values here. 9 multiplied by 10 raised to 9 Okay, 1 upon 4 pi epsilon naught is 9 multiplied by 10 raised to 9. And Q is how much? 3.2 multiplied by 10 raised to minus 7. And the R is 15 centimeters. So it is 15 centimeters square. So 15 multiplied by 10 raised to minus 1. And we have square of that. I'm sorry. So this is equal to. Now I can write this as 90 multiplied by 10 raised to 8 divided by, I have 15 multiplied by 15 multiplied by 10 raised to minus 2, and in numerator it is 3.2 multiplied by 10 raised to minus 7. Okay, so 15 6 are 90, right? So then you have 6. So I will take one more 10 out of 10 raised to 8. So I will make it 60. So it is 60 times 10 raised to 7 multiplied by, you have 3.2 multiplied by 10 raised to minus 7 and divided by 15. So this 10 raised to plus 7 and minus 7 gets cancelled out. 16 divided by 15 is 4. 4 times 3. Oh, we have got this 10 raised to minus 2 also. We have to take it in to the numerator. Okay, so it becomes 10 raised to plus 2. So we have 4 times 3.2, that is 12.2 multiplied by 10 raised to 2. So it should be 12 point something multiplied by 10 raised to 2. Am I correct or I'm not correct? Oh, this is centimeters, right? It is not 10 raised to minus 1. No, it's 10 raised to minus 2 in meters. This is 10 raised to minus 4. If you take it to numerator, it becomes 10 raised to plus 4. Okay, I'm sorry. So it is 12 multiplied by 10 raised to 4. That is 1.2 multiplied by 10 raised to 5 newtons per coulomb. It is option B is the answer. Right, centimeters to meters. Okay. All right. So this is very, very simple question. Okay, and it's recent one. It cannot be simpler than this, right? Let us see next question. A thin conducting ring of radius r is given a charge plus q. So you have given charge plus q to this ring. The electric field at the center O of the ring due to charge on part AKB due to this part is E. Okay, electric field due to this part at the center is E. The electric field at the center due to charge on part ACDB of the ring is. Can you guess? Alright. How much would be electric field at the center of the ring? Charge Q is given to the ring. How much would be the electric field at the center? So let's suppose we have this ring. How much would be charge at the, sorry, electric field at the center? It must be zero, right? It must be zero. How? Because if you consider a small length element here, okay, it will produce its electric field, and that electric field will be directed like this, okay, in this direction. It will be in this direction, okay. But then you can consider a length element having same length. That means charge on this one and charge on this one is equal, okay. The charges are equal. Therefore, electric field due to this one is suppose dE. The electric field due to other one will also be equal to dE. They will have same magnitude, but they will be opposite in direction. Okay, this is the electric field due to this length element. This one is the electric field due to this length element. It is radially outwards, right? So these two electric fields, they will cancel out each other. Okay, so net electric field would be 0, right? Net electric field would be 0. I mean, you can consider such small length elements over the total length of this ring. So if you consider a length element here, its electric field will be directed like this. Then you can consider a length element here whose electric field will be directed like this, exactly a diametrically opposite point. Okay, so their electric field will get cancelled out. Then you can consider a length element here and here, their electric fields will get cancelled out. Okay, so net electric field at the center of ring will be 0, right? So question is, you are giving some charge, okay, then the electric field due to this much part is E. Okay, electric field due to this much part is E, right? So there is some positive charge on this part. What will be direction of this electric field? It will be directed like this. Okay, from this part to radially outwards towards the center. We can say this is the direction of electric field due to this part. Okay, the electric field at center due to charge on the part, this remaining part ACdV would be. Okay, you answered already, right? E along OK, right? It's correct. Okay, so electric field due to this part and the electric field due to remaining part, they should cancel out each other. Okay, so electric field due to this part is directed from K to O. It has got magnitude E. Electric field due to remaining part must have magnitude equal to E, and it would cancel out the electric field due to this part. Okay, so it's correct, right? There is one more way to think that electric field at the center would be 0. What way? We have the formula, right? E equals to 1 upon 4 pi epsilon naught q multiplied by x divided by r square plus x square raised to 3 by 2. So if you have a ring, the electric field on the axis of the ring, it is given by this formula. Okay, it is given by this formula. So x is distance from the center. If x is 0, then electric field is 0, right? Next question. Electric field at center O of semicircle of radius a having linear charge density lambda given as. So we have discussed this yesterday. This is direct formula. Tell me. It is option C. Okay, it is option C. Lambda divided by 2 pi epsilon naught A. Next question is, a square surface of side L meter in the plane of paper is placed in uniform electric field E volts per meter acting along the same plane at an angle theta with the horizontal side of the square as shown in the figure. The electric flux linked to the surface in units of volt meter is. So a square surface of side L meter in the plane of paper. It is in the plane of paper. In uniform electric field E acting along the same plane. So electric field is acting along this plane. Okay, it's like electric field is acting along this plane, and you are keeping, okay, there is electric field like this, and you are keeping a square paper. Okay, both are in same plane. So how much would be the electric flux passing through this paper? See, your paper, okay, this is the paper. Okay, so this is the paper. It's in some plane, and electric field is passing like this. Okay, along that plane only. So no lines are passing through the plane, through the paper. Okay, the electric field lines are passing like this only, right? So the answer is 0. Okay, there were many questions like this. Okay, in Neet and in some other medical entrances. This is another question from Neet itself. a square surface of side L meters is in plane of the paper. Okay. A uniform electric field E bar volt per meter also in the plane of paper is limited only to lower half of the square surface. See the figure. Then the electric flux in SI units associated with the surface is. Again, answer is 0, right? This is exactly similar to the last question. Okay. So actually there were this 4, or maybe there would be another question in last year or something. So 4 to 5 questions were there only. Okay. Let's see some more questions. So in a region, the intensity of electric field is given by, this is the formula. Okay, sorry. In a region, the intensity of electric field is given by E bar equals to 2I cap plus 3J cap plus K cap in newtons per coulomb. The electric flux through a surface S equals to 10 I cap meter square in the region is. Actually straightforward question, but there was no question like this asked in the NEET exam, but there can be a question like this. Okay, can be asked. So we know flux is equal to what? It is dot product of E bar dot A bar. Or here the area vector, it is denoted by S. So it is E bar dot S bar. Okay. So it is 2I cap plus 3J cap plus K cap. It's dot product with 10I cap. So it is x component multiplied by x component, y component multiplied by y component, z component multiplied by z component. But we don't have y and z components in S bar. It is just 10 multiplied by 2. So answer is 20. Okay. Answer is 20. And what would be its unit? So unit is Newton per coulomb multiplied by meter square, we can say. Okay. Newton per coulomb multiplied by meter square, or Newton meter square per coulomb. This is the unit. All right. Very simple question. There exists an electric field of 1 Newton per coulomb along y direction. The flux passing through the square of 1 meter placed in the xy plane inside the electric field is. So it is from J&K, Jammu and Kashmir CET. Okay. All right. I didn't understand it. I just read the question. Okay. So there exists an electric field of 1 Newton per coulomb along y direction. So there is an electric field of 1 Newton per coulomb along y direction. The flux passing through the square of 1 meter placed in xy plane inside the electric field is. Okay, so you have square of 1 meter, but it is placed in which plane? So this is y direction, this is x direction, and the square is kept in xy plane only. Okay, it is kept in xy plane only. So plane of the electric field and plane of that square, they are same. Both are lying in the same plane. So we don't have to calculate electric field. It is electric flux. It is 0. Okay, the flux passing through the square of 1 meter placed in the xy plane. It is 0. Right? So in some questions diagram is drawn, in some questions it is direction is given, but the meaning is same. Okay, the questions are similar. Okay, next question. So either there will be questions like this or there will be questions like this. Okay, electric flux emanating through a surface element ds equals to 5I cap placed in an electric field. This electric field E equals to 4I cap plus 4J cap plus 4K cap is. So it is very simple. Flux is I is equal to E bar dot area bar. Okay, that is ds bar, and it is 4 I cap multiplied by 5 I cap, so it is 20, right? Newton meter square per coulomb. So, okay, in some arbitrary units are not given, so it's 20 units. Option B. Next question. A cube of side L is placed in uniform electric field E, where E is equal to E multiplied by I cap. The net electric flux through the cube is, okay. So electric field is directed like this. The electric field is directed like this along x-axis. It is E multiplied by I cap, and you keep cube here. So this is the cube. Question is, how much would be the flux due to this electric field through this cube? So can you guess how much would be the flux? Okay. The answer would be zero only, but let me explain how. So let's name this cube. Let's call it ABCD or EFGH PQRS. Okay. So let's name it EFGH PQRS. So now the electric field lines, they will enter this cube through this phase. Okay, through which phase? EFGH. Okay. So this is some area, and there will be an area vector associated to this area. So how do we choose the area vector, direction of area vectors? So it is perpendicular to plane of area, right? But now there are two possible perpendiculars, two possible directions of perpendiculars. Okay. So the thumb up rule is, if it is a closed surface, then we consider outwards area vector. Okay. A perpendicular which is outwards from the surface. It is directed outwards from the surface as an area vector, as the direction of area vector. So what is the direction here? So the direction is like this. Okay, so this is this area, which one? EFGH. So this is A cap. Okay, this is, sorry, A bar. Okay, and for this area PQRS, for this area, the area vector will be directed like this, outwards from the plane of area. It is closed surface. The area will be directed outwards from the plane of area. Okay, so it is directed like this. So let's call this A dash bar. Now it's clear that magnitude of this area and this area is equal. Okay, this area and this area, they are same areas, actually same amount of areas, right? But their directions are opposite. So now how much would be flux through this area? How much would be flux through this area? So I can say flux through A. Flux through A, through A, let's call it phi A. It's equal to E bar dot A bar. Okay. So this is E into I cap. Field is along positive x-axis. A bar is directed along negative x-axis. Right. So it is E multiplied by I cap dotted with A multiplied by minus I cap. Okay, so it is E multiplied by A multiplied by I cap into I cap. is 1, but we have this negative sign. So it is minus of EA. Okay. And similarly, flux through this area, not B, flux through A dash is equal to E bar dot A dash bar. So it is E into I cap dotted with A multiplied by A dash multiplied by I cap. Or we can say its magnitude is just equal to A, right? Magnitude of A dash is equal to A dash bar is equal to magnitude of A bar. Okay. This is I cap multiplied by I cap is 1. So this is equal to what? E multiplied by A. So now, what is the total flux? What is the total flux? Total flux is phi A plus phi A dash. So sum of these two is 0. Okay, total flux is phi A plus phi A dash, and it is equal to 0. This is total flux. Okay, got it? Yes, no? All right. So another way to think about this is geometrical picture. So you have some closed surface. Electric field lines are entering that surface. Okay, there is no charge inside that surface. Electric field lines are entering that surface from one side. They will leave from other side. Okay, whatever field lines enter from this side, they will leave from the other side, right? So flux from this side is negative, suppose, or it has some direction. Okay, so flux for entering lines, suppose it is positive, then flux for negative lines would be negative and amount is same, right? So therefore, that positive and negative flux is equal to what? 0. If a closed surface does not enclose any charge, there is no charge enclosed, okay, there is no charge inside a closed surface, then the flux through that surface due to outer electric field, okay, the electric field which is generated by charges outside of that surface is always 0. Okay, so let's see next question. In the figure, the net electric flux through area A is phi equals to E bar dot A bar. When the system is in air, the on immersing the system in water, the net electric flux through the area. Option A becomes 0, option B remains same, option C increases, option D decreases. Tell me. Option D decreases, right? And the reason? Because the magnitude of E bar will decrease, right? E bar in air is 1 upon 4 pi epsilon naught multiplied by, if there is one charge, there is one charge actually, okay. So in fact there is one charge, so Q upon R square multiplied by some unit vector, okay, R cap. Electric field in water would be what? 1 upon 4 pi epsilon naught K. So it is 1 upon 4 pi epsilon, right? So which is equal to epsilon 0 K. The dielectric constant of water is K. Okay. So for all other medias, the dielectric constant is more compared to that of air. Okay. Right. For air it is 1, almost 1 we can say. For other medias it is greater than 1. So therefore electric field in other medias decreases. Okay. And that's why flux will decrease. In a region of space, the electric field is given by 8 I cap plus 4 j cap plus 3 k cap. The electric flux through a surface of area 100 unit in xy plane is. Tell me. Let's draw coordinate axis. So this is x-axis, or yeah, let's call this as x-axis, this as y-axis, this one as z-axis. So then the electric flux through area 100 units. So let's consider an area, any area in xy plane. So this is any area in the xy plane, or we can draw it parallel to xy plane also. So it makes no difference, right? So let's consider an area in the xy plane. Now suppose the origin of electric field is at this point only. Okay, let's just suppose that origin of the electric field is at this point. So the electric field will have three components. The electric field will have three components. One is Ex, one is Ey. Alright, that was Y. One is Ex, one is Ey, and one is Ez. Sorry, Ez. So out of these three components, the Ex, Ey, and Ez, which component of electric field is actually cutting the area? Alright, you already answered. Okay, so yeah, that's correct. Okay, so it is 300 units, right? So area vector is in xy plane, only z vector or z component of electric field will cut it. Okay, that's why there will be flux due to the z component only. Okay, so answer is it 300? Right, right. Z component is 3. Okay, 3 times 100, 300 units. Right. Okay, very good. The electric flux phi through a hemisphere surface of radius r placed in a uniform electric field E parallel to the axis of its circular plane is 2 pi r e, 2 pi r square e, pi r square e, 4 by 3 pi r cube e. So there is a hemisphere. So let us draw a hemisphere. It would be something like this. Okay, this is a hemisphere. This is not, but let's just let us just suppose that this is a hemisphere, half of the sphere. Okay, and this is axis of the hemisphere, right? So it passes through the center of this hemisphere, and given is the flux, okay, through this hemisphere due to the electric field parallel to the axis of circular plane. So it is parallel to axis of circular plane. This is the circular plane, and it's parallel to this axis. Okay, so this is suppose the electric field like this, E1. So how much would be the flux? It will be pi r square E only. All right. If it was a closed surface, then answer would be 0. But now see, we can say whatever number of electric field lines they go through this much area, they pass out of hemisphere, right? So the electric flux is number of electric field lines passing normally through an area. Okay, it is E bar dot A bar. So whatever electric field lines are entering this region, they will only pass through this hemispherical surface, right? Okay, so effective area of this hemispherical surface is how much? It is just pi r square. Okay, it is this much area only, pi r square. Okay, whatever number of field lines enter through that region through pi r square, they only go out of this hemispherical surface. They only eject out of hemispherical surface. Okay, so how much is the flux? Flux is equal to pi r square multiplied by E, or E multiplied by pi r square. Get it? Yes, no? Let's see next question. A positively charged thin metal ring of radius r is fixed in the xy plane with its center at origin O. So we have positively charged thin metal ring of radius r. It is fixed in xy plane with its center at O. A negatively charged particle P is released from rest at point 00z, where z is greater than 0. Then the motion of P is option 1 accelerated along a straight line, option 2 simple harmonic for all values of z satisfying 0 is less than z is less than infinity, option 3 approximately simple harmonic provided z is very small compared to r, and option 4 such that P crosses O and continues to move along the negative z axis towards z equals to minus infinity. So now this is very good question. Okay, and I like this question. See, there is a ring, okay, a metal ring which is fixed in the xy plane. So once again, let's imagine xyz axis. So these are xyz axis, and the metal ring is placed in the xy plane. This is the metal ring. It has got some charge. Charge equal to what? It is positively charged metal ring. Okay. So charge is suppose small capital Q, right? So this is suppose the center of the ring. Then there is a negatively charged particle P released from rest at point 00z. So this is x, this is y, this is z axis, and the particle is released from 00z from this point. Okay, right? X coordinate is 0, y coordinate 0. So this is particle P. So it has got charge minus Q. So now what will happen? See, there is some electric field due to this ring at this point. So how much would be the force? So force is given by electric field due to ring on the axial point multiplied by the charge. Charge is minus Q. What is the formula for electric field? It's 1 upon 4 pi epsilon naught multiplied by Q multiplied by X. But here it's along Z axis. So instead of X, we'll have Z. So Q into Z divided by R square plus X square. But we have Z instead of that raised to 3 by 2. This is our formula. Right? Sorry. Oh, okay, this is our formula of electric field multiplied by we have minus Q. This charge minus Q. Okay. So now see what happens. So it is accelerated. I'm sorry. It is accelerated along a straight line. Okay, this is the first option. So actually it will get accelerated like this. Okay, but it will reach the center and pass on the other side. Once it passes on the other side, what will happen? Then the ring will attract it along this direction. Okay, at center the force will be 0 because z, when z becomes 0, the force becomes 0, right? So the force is maximum here, then it goes on decreasing, it becomes 0. But when this charge passes on the other side, what will happen? Again the force will be towards center, right? Okay, so see, how can I say that? Here you can take everything else common. Okay, so Q is a constant 4 pi epsilon naught, constant, small q constant. You can take it out. So Q multiplied by Q divided by 4 pi epsilon naught, you can take out. So force is directed along minus z divided by r square plus z square raised to 3 by 2. This is the denominator. Okay, so forget about denominator also for a minute. Okay, so it is directed along minus z. So what is minus z? It's downwards direction. Okay, So when z is positive, it is directed along minus z. When z becomes negative, if charge goes on the other side, z becomes negative, the force will be directed upwards. Okay, because z itself is negative, negative times negative, okay, will give us positive. So force will be directed upward. So it is always directed towards the center of the ring. Okay, right? And then now, is the motion simple harmonic for all values of z? So answer is no. Why? When z becomes large, this denominator will also dominate. The nature of force, if force is directly proportional to minus of z, okay, in simple harmonic motion, we have force directly proportional to what? Displacement, but it is directed opposite to displacement. Okay, so when force is directed to minus z, then only it will be simple harmonic. Okay, for all values of z, it cannot be simple harmonic. Now, z is very, very small compared to r. Then what we can do is, we can neglect the z in the denominator. So denominator is simply r square. We can take that also outside. Okay, so everything else would be constant when z is very, very less compared to r. So this is equal to k times minus z. What is that constant? Everything else. When z is very small, we'll neglect z in denominator. Okay, so all these becomes a constant. Okay, so it is k times minus z. Force is equal to k times minus z for that. And that means when z is small, this force is like a spring force. Okay, this is a Hooke's law. Okay, so anything which follows Hooke's law performs which kind of motion? It performs simple harmonic motion. Okay, so answer is option 3. Right. So let us solve some problems based upon the electric flux and the Gauss's law. So let's see this problem. What is the flux through a cube of side A if a point charge small q is at one of its corner? So this is very, very simple. Can you tell me? And this question is repeated quite a lot of times. See, question is, what is flux through a cube of side A if charge q is at one of its corner? So see, suppose I draw cube like this and charge is kept here at one of its corner, right? So now we know the Gauss's law. Gauss's law tells us that the flux through any closed surface is equal to what? Charge enclosed by the surface divided by epsilon naught, right? That's Gauss's law. Phi is equal to q divided by epsilon naught. Okay, charge enclosed divided by epsilon naught. So this is charge q. Now here we have to think how many cubes like this you have to keep around this charge so that the charge gets enclosed. Okay, so here, see, this is one cube, then I will need 8 such cubes. See how? Okay, this is second cube, this is third cube, this is fourth cube. Okay. So now charge is still not fully enclosed. Now I want to cover this charge completely. Okay, so I have to keep 4 more cubes like this on top of this charge. Okay, so I will keep 4 more cubes like this. Sorry, such that the charge gets fully enclosed. Okay, so let me use some different color for this. No, I hope you can see this. If I keep 4 more cubes like this, the charge will get fully enclosed. Right, 4 cubes, and just like that 4 more cubes if I keep on top of that charge, it will get fully enclosed by these 8 cubes. Okay, so now flux through these 8 cubes is equal to what? Q upon epsilon naught. So flux through one of those 8 cube will be equal to what? Flux through one of those 8 cube 8 cubes will be equal to 1/8. It will be 1/8 of this pi. That is 1/8 of q divided by epsilon naught. Right? So option B is the answer. Got this? Yes, no? Okay, good. Let's see next question. A charge q is enclosed by a Gaussian spherical surface of radius r. If the radius is doubled, then the outward electric flux will increase 4 times, be reduced to half, remain the same, be doubled. Tell me. Charge q is fully enclosed by a spherical surface of radius r. Okay, this is the radius r. Now, if you increase the radius, so now suppose you take some other sphere having twice as much the radius. Okay, so question is, what will be the flux through this second sphere? It will be same, right? It remains the same. Option C. Okay, this is simple. Next question. A hollow cylinder has a charge q coulomb within it. So there is charge of q coulomb within this hollow cylinder. Then if phi is electric flux in units of voltmeter associated with curved surface B, so flux coming out of the closed surface B is phi. This is given. The flux linked with plane surface A, we want to find out flux through surface A in units of voltmeter will be. So this is also a simple question. See, the net flux we can say is equal to flux through B plus flux through A plus flux through C. Okay, and flux through B is given. Flux through B is phi. Right, flux through this surface, covered surface, is phi. So this is phi, and flux through A and flux through C will be equal, right? Whatever number of field lines they pass through this surface, same number of field lines will pass through the surface C also. Okay, so we can say that phi C is equal to phi A, right? So this we can write as 2 times of phi A. Okay, and what is total flux coming out of this cylinder? What is the total flux coming out of the cylinder? It is equal to q upon epsilon naught, right? According to the Gauss's law. Okay, so therefore we can find out phi A using this. What will be phi A? So we can take this phi on the other side. So we get 2 times phi A equals to q divided by epsilon naught minus phi. And we can take this 2 on the other side. So we get half of q divided by epsilon naught minus phi. This is the answer. Option D is the answer. A charge q is located at the center of a cube. The electric flux through any faces. So you keep charge q at the center of a cube. The question is electric flux through any surfaces. Okay. So this is simple. Tell me, how many faces does the cube have? 6 faces, right? Okay. So flux through any face would be what? Total flux phi is equal to q divided by epsilon naught according to Gauss's law. So flux through any surface will be what? Flux through any surface, let's call it phi dash, will be q divided by 6 epsilon naught. This is the answer. It's not there. 2 pi q divided by, okay. All right, they have written it in some other way. Okay, is it B? 4 pi gets cancelled. Q divided by 6 epsilon naught. Right. This is the answer. Okay. Let's see next question. A charge Q microcoulomb is placed at the center of a cube. The flux coming out from each phase will be. So again, this is also a simple question. So flux through the cube is Q divided by, it is Q microcoulomb. So it is Q multiplied by 10 raised to minus 6, right? Divided by epsilon naught. Okay, in terms of coulombs, right? Charge in terms of coulombs is Q multiplied by 10 raised to minus 6. So phi dash will be what? This divided by 6. So it is option A, right? These questions are very simple. Next question. A charge Q, a charge Q is situated at the corner of a cube. This is repeated. Okay. The electric flux passed through all 6 spaces. It is Q divided by, so option B. It is at the corner. Charge is at the corner. Okay. We saw first question, which was actually exactly this question only. So option B. Shall I explain it? Shall I explain it? Let's see next question. A point charge plus Q is placed at center of a cube. Again repeated. The electric flux emerging from the cube is. Tell me. Total flux. It's just Q divided by epsilon naught. Option D. Right. Next question. A hollow metal sphere of radius r is uniformly charged. It's a hollow sphere, okay? The electric field due to the sphere at a distance r from the center. Option A decreases as r increases for r less than r and for r greater than r. Increases as r increases for r less than r and for r greater than r. 0 as r increases for r less than r, decreases as r increases for r greater than r. Okay, 0 as r increases for r less than r, increases as r increases for r greater than r. Tell me. It's a hollow sphere. It's a hollow sphere. So electric field inside the hollow sphere is I'm sorry, it's 0, right? Field inside is 0. So it's 0 inside. So option C and option D tell that R 0 as R increases for R smaller than R. Okay, R smaller than capital R. The electric field is 0. And then option C is saying it decreases as small r increases for R greater than capital R. And option D is saying it increases. So obviously, as you go away from the sphere, it goes on decreasing. Okay, so option C is the answer. All right. Two parallel infinite line charges with linear charge densities plus lambda coulomb per meter and minus lambda coulomb per meter are placed at a distance of 2r in free space. What is the electric field midway between the two line charges? Okay, you have two line charges. So this is one, this is, sorry, should be straight. Okay, this is one, this is second one. And the distance between these two, how much is distance between these two? It is 2 times r. So this distance is 2 times r. Okay. And you want the electric field at this point. So, for first one, the linear charge density is plus lambda. For the second one, it is minus lambda. So can you guess? We want electric field at this point, P. Okay. So let's find out electric field due to this one. Let's call it E plus bar. And electric field due to the sorry, other one is E minus bar. Net electric field at that point would be addition of E plus bar and E minus bar. What is direction of electric field due to this what line charge? It is outwards like this. Okay, perpendicular to the length of line charge. Okay, so it is towards point P. So E plus is towards point P, right? It is towards point P. What about E minus? So E minus is, it is away from point P. If you keep a small positive charge here, it will get attracted by the other line charge. Okay, but both of them, they are in same direction. That means the net electric field will get added. Okay, so E is equal to what? You can say E plus plus E minus, that is lambda divided by 2 pi epsilon naught r plus lambda divided by 2 pi epsilon naught r. We already considered the direction. Okay, so now we are considering magnitude only. So it is 2 lambda divided by 2 pi epsilon naught r, or lambda divided by pi epsilon naught r. Okay, so it is option D. Right, it's option D. Okay, so yeah, this was the toughest question till now, right? Okay, this is also easy, but this was toughest question out of these. Anyways, next question. The electric field at a distance 3r by 2 from the center of a charged conducting spherical shell of radius r is E. So the electric field at 3r by 2. So let's call r equals to 3r by 2. So electric field at r is equal to E for a charged conducting spherical shell. The electric field at a distance r by 2 from the center of the sphere is. Tell me. You have a conducting shell. What is electric field at r by 2? This is a shell. This is distance r, and this is the point P. It can be anywhere. It is inside, right? Electric field inside the conducting shell is 0. Okay, so option A. So in last question, they tried to confuse. Okay, they gave the electric field at 3r by 2. It's a shell. Electric field at 3r by 2 is something, and tell us the electric field at r by 2, right? Anyways, next question. A hollow insulated conduction sphere is given a positive charge 10 microcoulomb. What will be the electric field at the center of sphere if its radius is 2 meters? Again, this is a repeated question. Answer is 0. It's a hollow sphere. Okay, so electric field inside is 0 if charges on the sphere. Okay, next question. Which of the following plots represent the variation of electric field with distance from the center of a uniformly charged non-conducting sphere of radius r? Tell me. It's not spherical shell. Okay, so If it was spherical shell, then answer would be what? Option A. Electric field inside, that is from 0 to R, electric field is 0. After that, it falls off inversely as R square. Okay, but it's a sphere, a solid sphere. So that's why it's option D. Yeah, if it is hollow sphere, the graph looks like this. If it is solid sphere, the graph looks like this. Okay. Next question. Two infinitely long parallel conducting plates having surface charge densities plus sigma and minus sigma respectively are separated by a small distance. The medium between plates is vacuum. If epsilon naught is the dielectric permittivity of vacuum, then the electric field in the region between the plates is. Again, this is similar to the other question that we saw. Okay, there were two line charges. Okay, two wires. So this is similar to that question. Here we have two plates. This is positively charged plate and there is one negatively charged plate like this. This is negatively charged and the surface charge density is plus sigma and minus sigma. So we want the electric field inside of these two plates. So the electric field will be, you can call electric field due to positive plate as E plus, due to negative plate as E minus. Okay. So electric field due to positive plate will be towards this point, okay, directed away from the positive plate towards the point. Electric field due to negative plate will be directed from this point towards the negative plate. But they are in same direction, right? If you think what will happen if you keep positive charge here, it will move towards right. The positive plate will push it, negative plate will pull it. Okay. So the net electric field is just E plus E minus, and this is just sum of magnitudes now because we have already considered the direction. So it is sigma divided by 2 epsilon naught. This is electric field due to a charged conducting plate plus sigma divided by 2 epsilon naught. So it is 2 sigma upon 2 epsilon naught, or you can say sigma upon epsilon naught, sigma divided by epsilon naught. So it is option C. Okay. All right. Let's see next question. The electric intensity outside a charged sphere of radius r at a distance small r greater than capital R is. Okay. So what is electric intensity outside a charged sphere? So see, suppose this is our charged sphere. So there is some charge on this sphere. Let's call the charge Q. Although we had found out the formula, okay, but uh, we can calculate it very easily. So see, electric field at distance r. So for any point outside this charge sphere, it behaves like what? It behaves like a charge only which is kept at the center here. So, so we can say electric field is just equal to 1 upon 4 pi epsilon naught multiplied by q divided by r square. Okay. So now this is, oh, they haven't given. Okay. So if this is a hollow sphere, then charge will be distributed on the surface of the sphere. So electric field is given by 1 upon 4 pi epsilon naught multiplied by q can be written as what? So we can write sigma because they have given sigma. It means it is a hollow sphere, right? Charge is distributed on the surface. So sigma is equal to q divided by 4 pi r square. Okay, take 4 pi r square on other side. So we can write that q is equal to sigma multiplied by 4 pi r square, where r is the radius of the sphere, divided by r square. Okay, small r square. So 4 pi gets cancelled out. So it is simple. It's sigma r square divided by epsilon naught r square, small r square. Option A. Right. So again, this was also a simple question. So we have found this formula. Okay, so you need to remember this one also, right? I mean, you need to remember, you need to memorize all the formula, all the formulae. Okay, all right. Let's see next question. The electric field in a certain region is acting radially outwards and is given by E equals to AR. Electric field is equal to AR. A charge contained in a sphere of radius A centered at the origin of field will be given by. Okay. All right. So the electric field in region is given by E equals to, sorry, E equals to A times R. And we want to find out charge enclosed, charge enclosed in a sphere of radius A. Okay. So here, let's suppose this is the sphere of radius A, and we are supposed to find out charge enclosed in this sphere. Okay. So see, the electric field is A times R. What will be electric field on the boundary of the sphere? So what will be electric field at this point? What will be the magnitude? Let's call this point P. Okay, electric field at point P will be equal to what? It is A times R. So here it will be A times A, small a, radially outwards. Okay. Then how much would be the flux due to this electric field? So flux due to electric field phi is equal to, it is the electric field multiplied by area. Okay, area of sphere we can say. So it is electric field multiplied by area of sphere, which is 4 pi a square, right? So we can substitute that. So it is electric field is a multiplied by small a multiplied by, we have 4 pi a square. It is a times a square is a cube, and this is equal to charge enclosed divided by epsilon naught. So we can move epsilon naught on the other side. So we get charge enclosed is epsilon naught 4 pi a multiplied by a cube, right? A cube. So this is the answer, or 4 pi epsilon naught a multiplied by a cube. So it is option C, right?